All right, recording is rolling. So, welcome to Wednesday, April 19th. You guys remember yesterday you took a quiz? Still got some students that need to take that and are also absent today, so haven't put those back yet, but haven't given those back yet. I'll let you post the solutions, of course, like I always do. But um, if you did it yesterday, then your grade is already on focus. So you see it there. Right? Also, yesterday I threw a couple of challenge questions on the board in case you happen to finish your quiz early. So we're going to go over these here in a minute. Then we're going to switch over to AP class, and we're going to do something that we've done in the past for kinematic motion. Actually, I prepped that and then realized, oh, actually, we already did that a few weeks back. All right, so I'm going to pull up a bunch of Unit 2 questions, multiple choice type, right, and we'll go through. I just hand you guys a blank quarter page. I'll have you guys keep track and then see how you do there. There are some review videos that are just posted to AP class. In fact, let me do this. I'm going to show you guys this. Let me switch my screen over, show you guys exactly what I'm talking about. All right. So, oh no, it's not going to show me that. Well, here, let me see if I can. I have it on my screen. It gives me more options. It like expands it out here. Let me try this. All right, hold on, it's taking a while to load. All right. All right, so at least on my other screen, I have a tab on the left side I can pull out, and there are review videos that a couple years ago and also last year they posted, but these they just posted, I think, last day or two. I went ahead and assigned them to you guys. This isn't going to be for points, but if you want an extra resource, you guys know the AP exam's in a few weeks here. All right, so so these are all up here. You might be able to access the other ones. Let me see if I can on my other screen over here. Pull up where those are. All right, there's a tab that says course resources, which I can't show you because it's not showing up there. All right, and then under course resources says review. Let's see if I can at least navigate to this window. Right. So then, look at this. Got 2021, 2022, and 2023. Now, 2023 are the ones that I assigned. It says assign all, but I already clicked that just so that it pops up in your feed, so that it makes it really accessible. Okay. Again, not gonna force you guys to watch those, but they're there for you. Right? You guys might be able to access these too. I might end up assigning these also, maybe not all at once, so it's not like completely overwhelming, but you might be able to actually see them. Maybe let me know if you can't, but maybe in time next week or two, I might like hit the assign all just so that it pops up in your feed. Okay, is that all right? All right, so let's go back over here. Okay, so we're going to take the rest of this week to, okay, we're going to do these challenge puzzles today and then Dynamics 1. We may or may not finish this by the end of today. If we don't, then we'll do the rest of these tomorrow. I'll pull up some of our cues for you guys to round out Thursday and Friday. Right now, AP Classroom, there are 3 practice exams. You guys have taken 2 of them already, right? We're going to do the third one next week. So Monday and Tuesday. You guys will bring your laptops Monday and Tuesday? Right. So in class Monday, Tuesday, you guys will definitely bring your laptops then, right? Right. You guys have that either written in your planner or you already bring your laptop every day anyway, right? Okay. So Monday, Tuesday, and then we'll go over the solutions Wednesday, Thursday, Friday, right? That'll round that out, right? Soon after that, AP exams are starting. Now, AP Physics is one of the last exams, so I'm slated to proctor, I think like 3 of them or something. So there's certain days I'm not going to be here, but you know I'll have practice materials for you guys then. Okay. Any questions so far? What's going on here? All right. So let's look at these challenge questions from yesterday. Challenge questions from yesterday. Right. Yeah, fold this over because that has yesterday's date. So it's not confusing there. All right. So I pulled a question that would align with Unit 3, which has to do with, well, it's like an orbits type question, right? Some kind of centripetal force type involved. Right? And then a question from Unit 1. Right? I have the solutions all worked out just off screen here. Yeah, everything works. Right? So I don't know, since you guys did have a chance to also see it yesterday and a few minutes today, has anybody got the answers to either of these questions? Either of these questions? Which guy?
I just solved for the first one on my calculator. Is it roughly 250,000?
I got something a little different. Maybe like one small error somewhere along the way. Okay. Also the first one actually does have an actual answer. So I did check on Google, and mine's like within like 1% or something like that too. So okay, all right. Anybody else think they may have got the solution to either one of these? All right. Well, here, let's start walking through it. And again, most importantly is the thought process. So, I mean, if it's like 10 different steps and you got 9 of them right and you missed like one little thing, then like, by AP's book, you could probably pick up a bunch of FRQ points, right? So I gave you some values like mass of the Earth, radius of the Earth, the time period of the Earth. Now, this would be for one rotation, right? Would be 24 hours. I went ahead and gave you guys, okay, that is 86,000 seconds, right? 86,400 seconds. Now, AP wouldn't, AP usually doesn't pitch questions exactly like this, although to answer AP questions, you have to have the same knowledge base, right? AP likes to ask more conceptual questions or questions that you can answer within 2 minutes, right? Because you get an average of 2 minutes per multiple choice question, right? So maybe this is you can stretch your imagination a bit more than AP might ask, but that's a good thing to do, right? Like if you can do something more challenging, you can definitely handle whatever AP throws at you. Right? So where could you put a satellite into geosynchronous orbit? Well, I guess you'd have to know what this means, but I think you might. Because what does geosynchronous mean? Yeah, revolves with the Earth, right? Okay, so you guys probably either knew that or could have figured that out, or I think I may have mentioned that maybe like last semester. So like here's the Earth, right? Here's the satellite, right? So now most satellites are I shouldn't say most, I don't actually know, right? But like International Space Station, I know is in low Earth orbit, which is actually like right about here, not too far off from the surface of the Earth. In the big scheme of things, it's like 400 kilometers up, which is not very large in terms of Earth's radius. But geosynchronous is like way out here, where it would take how long to go around once? 24 hours. Which would match the rotation of the Earth, right? Right? Take 24 hours to go around. So, how far out do you have to have this to make it go 24 hours, right? And actually, technically the question I asked was at what altitude. So if you know this distance, then here, let me plate this draw in here. Okay. I'll call capital R the radius of the Earth. I'll call lowercase r the distance to the satellite from the center of the Earth, right? Because we're always measuring center to center, right? And physics, right? And I'll call h the altitude, like a height. Right? Call that a h, right? And that was really the question. So could you guys say that that altitude is the distance to the center of the Earth minus the Earth's radius? Right? That could be like the last step. Right now, there's a bunch of steps that lead into that, but that's kind of like the final step. Yeah. All right. So that's the last leg of the journey. But where are we going to start this thing? Right? Where do you guys think we should start? What's the first step you should write? How about this? Has something to do with orbits, right? Does anybody know a formula for orbital speed, maybe? Orbital speed? Yeah, what you got?
Square root of GM over R.
Square root GM on R. Okay. Now, okay, so you're saying orbital speed is square root GM on R. Right? Now, I want to write that down, except are you allowed to just pull that out of your back pocket and throw that down on an FRQ just out of nowhere? Or do you have to sort of derive that in a couple of steps?
You derive that?
Yeah. And how do you derive it, right? So there's like a couple steps that lead into that expression, right? So how do you show that that's what orbital speed is for a circular orbit? Boom. Yeah. You guys hear Scarlett? Is centripetal force is provided by the gravitational force. Okay? That's what I say. I say the centripetal force to hold that satellite in a circle, right, is provided by the Newtonian gravitational force, right? And these have expressions. So what's the expression for centripetal force? Yes, Stu? Boom. Yeah. All right. Yes, you guys heard Studi. We got mv squared over. Now I'm going to use lowercase r, right? So that it matches the picture that I drew. Where's the picture I drew? We're talking about from the center of the Earth to the satellite. Right? Oh, guys, which mass is this? Is this mass of the Earth or mass of the satellite? Mass of the satellite. So maybe I'll call this little m, and I'll call the mass of the Earth big M. Is that okay? Okay. All good. Okay. And that's equal to. And what was universal gravitation? What's that? GMM over r squared. Right? Remember that? Right. if you just had gm over r squared, where m is the mass of the Earth, that's a gravity field. It could be like 9.8 meters per second squared for Earth. If you throw in the other m, oh, now you have a force, right? F equals ma kind of deal. All right, and okay, so we have this expression set up. What are we solving for here? Yeah, this velocity. I could say a tangential velocity. You could also call it speed, right? Because it is constantly changing direction, right? So is this a constant velocity? Not technically, because it's changing direction. There's a net force on it. There's a net force, the centripetal force, right? You could say constant speed. That'd be okay. That would be true for a circular orbit. Circular orbit would be constant speed. Okay. Okay. All right. Ooh, what cancels out on both sides? Yeah, the mass of the satellite. Right. So, which I didn't give you anyway. Maybe I should have, just as a red herring number, but it doesn't matter what mass satellite is. Right? If you have a bunch of satellites all different sizes, they could all be kind of like moving together. Right, so cross multiply an r, I guess one of the r's cancels, right? And then take the square root of both sides. So the orbital speed for a circular orbit is square root gm on r. That's exactly what I just said. Boom, and now you've derived it. Know how to do that. Look at that, guys, that's 3 steps. The setup, plug in the expressions, solve for v, boom, 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 right? There's a decent chance that that'll show up on an FRQ, and you'll have to know that. Okay, you guys see that? All right, next thing. What about this deal about like geosynchronous, which is 24-hour time period? And I helped you guys out a bit and said, well, it's 86,400 seconds, because seconds is the base SI unit for time. Right? How are we going to incorporate that into this? Where does that go? Yeah, wait. Yes, this is orbital speed. Right. Okay, yeah. So let me touch on this a little bit more. Right, so orbital speed. So G is universal gravity constant. That's 6.67 times 10 to the negative 11 newton meter squared per kilogram squared. Right. I think they should give that to you right here. Right. So AP will provide that to you. Although I don't know, I've never seen a question where they make you like reference it there, but it is there. Okay. Capital M is the mass of the planet that's being orbited. Right? And this lowercase r is the distance from the center of that planet. Right? So if you were in low Earth orbit, you'd have to go like really fast. Right? And if you're further away, you don't have to go as fast to stay in orbit. Right? But like International Space Station takes 90 minutes to go around. Ooh, that's whipping. Right? The moon is way further out. So it takes like an entire like 28 days or something to go around. Right? Right. So where are we going to fit in time period? Where does time period fit in? Yeah.
Bring it into the velocity term.
Yes. Yeah. So something to do with the speed, right? Because here, think about this. Whatever speed this is going at, I'll call this v, like a tangential speed, right? Has something to do with like maybe how long it takes to go around once, right? Okay. Because what is speed? Speed is what per what?
Meters per second.
Yeah, meters per second. Some kind of distance per time, right? Right. Distance per time. That'd be like the one time period. That's where that fits in. But how are we going to get this distance? What is the distance around?
2 pi r.
2 pi r, right? We're going to assume a circular orbit. Now, you might remember Kepler said, well, it's technically elliptical. It's not very elliptical. A lot of times we simplified it basically a circle, right? And that's pretty close, right? So we're going to say a circular orbit, circumference equals 2 pi r, right? So this orbital speed is 2 pi r divided by the time period. Okay. That's square root gm on r. Okay. Is this r this r? Yeah, it's the same r. Okay. Which I guess we're kind of solving for, right? Because the question is like, where do we park the satellite? Okay. Now, again, there is that last extension of the question we'll worry about later, but we do need to know where to park the satellite. That's the main premise that we're solving for, right? Okay. So we're kind of solving for this guy right here. He's showing up in 2 places. Okay. And what else do we have? Oh, okay, so 2 pi, that's a constant. I told you the time period was like 86,400 seconds. You guys know universal gravity constant, which I gave to you in the mass of the Earth. Oh, hey, look, it's all here, right? We just solve for this. So let's go to, well, I got to get these R's together so I can solve it. Now it's just an algebra quest, right? We've knocked out the main physics. The rest of this is just algebra, right? For the most part. So maybe square both sides to get rid of the square root. So it's like 2 pi quantity squared r squared over time period squared equals gm on r. Oops, like that, right? Maybe I could cross multiply the r and get r cubed. right? And then take the 2 pi quantity squared, divide it down, the t squared, multiply it up. So I'm getting r cubed is that g m t squared all on 2 pi quantity squared, like that. Wouldn't that be true? Right. And then what's the last step to solve for r?
The cube root of both sides.
Boom, take the cube root, right? Cube root. So r equals, right? I'm going to write it this way: g m t squared on 2 pi quantity squared raised to the power of, what is this? Power of what? Yeah, there you go. 1/3. Yeah, here, if you guys say that, right? That's one way to do it. Right. All right, now what does this look like with numbers? Right, yeah, that's part of the trick. Again, this is longer than a 2-minute question, right? But here, let's plug in some numbers here. Actually, here, I'm just going to show you guys my notes from yesterday just to save us a little time, because as long as you see the concept, as long as you can do that process that we've done so far, you're all right. So here's my notes from yesterday when I was solving this myself. Here's G. Here's the mass of the Earth. Here's the time period in seconds. Here's 2 pi quantity squared, all raised to the 1/3. And I got like 42 million sohm meters. Okay? Okay. Now, again, that's the distance from the center of the planet. Okay, you guys got that? Okay. So there is a little bit more to this. Okay. So let's finish this off here. Okay. Oh, this is what I told you guys at the outset would be like the last step that you do this, right? So the altitude is the distance that we just solved for minus the radius of the Earth, right? You guys see that? It's good to be able to like, conceptualize that, right? I think APS has asked questions where you have to like understand this concept, right? Right? And then so you subtract the radius of the Earth, and then that tells you the altitude, like how far above, right? Something else I might be interested in is like what is this ratio? Right? So like how many Earth radii does it take to get to that satellite? And it's something like 6 or something, like if you divide the numbers. But okay. Right. Oh, and then I checked on Google, and look at that. Right, here's my answer, but the numbers plugged in. Here's Google's answer, and look, it's like it's a near match, right? So, right, are we good with that one? Right. Right, so yeah, pretty complex problem, but you should be able to have the skills to be able to solve that. All right. Then there was this other challenge question I threw at you guys, which was from Unit 1, kinematic motion. Now I did pick a projectile, so I guess that was like the second half of Unit 1, right? Maybe the harder part, right? We're gonna blast a cannonball at this speed, at this angle from the horizontal. Where does it land? Right. So let's walk through this process. Now, big concept is this cannonball accelerating as it's flying through the air?
Downward.
Yes, downward, right? It has to be accelerating because it's on a curved path, right? Anything that's either speeding up, slowing down, or changing direction has to be accelerating. There's a net force on it. In fact, what is the net force equal to? Its own weight, right? Its own weight, right? Now, I didn't give you the mass of the cannonball because back in Unit 1, we didn't really even think about mass, right? Other than that, ends up canceling out in terms of kinematic motion. Right? Okay, so there is a downward acceleration. But what about across the field? Is it going pretty well constant speed across the field? Yeah, right? Very true. So check this out. We're going to break this into components. All my we're gonna say it's been blasted 100 meters per second at a 40-degree angle. My picture's not really to scale, but not exactly, but let's say it's about 40 degrees. I don't know, maybe it's not too far off. Right? Oh, what does this horizontal component represent? It represents the horizontal component of velocity. I could call it v sub x, right? The velocity in the x direction, right? And that's equal to what times what? Boom, 100 meters per second times cosine of 40 degrees. Okay? Let's get a number for that. What is 100 cosine? Right. My calculator's in degrees, not radians. Good, that's what I'm looking for. I'm looking at like 76.6 meters per second. Okay, rounded a little bit, but that should work. Right? Digits. And then, what does this vertical component represent? That's exactly what I was looking for. Right? the initial component of vertical velocity, right? So I don't want to just say Vy. I want to say Vy initial, or you could do V initial Y, right? The order of the subscripts. I've seen it both ways. Okay? Okay. So that's 100 meters per second. I'm sure you guys are figuring this out. Times what? Sine of 40 degrees. Okay. Which should be less than 76 meters per second because sine of 40 degrees less than cosine of 40 degrees. Here, I can just scroll up, scroll over, and where the cosine was, I can replace it with the sine. 64.278. I'll call it 64.3. How about that? 64.3, that'd be meters per second. Okay. Of course, that immediately starts changing as soon as it leaves the cannon barrel because gravity's pulling it down. Okay. 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 Now, well, let me throw a kind of a weird question at you guys, but maybe this will help frame the problem a bit. Okay. What if you turn gravity off? There's no gravity. What's that cannonball going to do?
Also vertical velocity.
Yeah, it's just going to have, just constant velocity, just straight lines. It's going to shoot into space forever, right? If there was no gravity, just fly in a straight line forever, right? So if we're trying to figure out where this is going to land, because we're thinking this is going to arc into a parabola shape and land somewhere downfield, right? Which component, horizontal or vertical, are we going to focus on to determine how much time it's going to be in the air?
Vertical.
Vertical, right? That's going to determine something to do with like a time constraint, right? So play around with this in your mind too, because I can see AP asking some version of this, right? Like if you aim it really shallow, it's not going to be in the air very long, right? Now it's going forward really fast, right? But it's not going to be there for very much time, right? So maybe it can't go very far. It goes like chunks like that. The more vertical you aim it, the more time it's going to be in the air, which make it go further, further, further. But the trade-off is that it has less horizontal component, so it's not going as fast horizontally, right? And in fact, if you aim it like really steep, like at an 85-degree angle, maybe it'll be in there a long time, but it's not going to go very far because it's not going to the right very fast. Right? So there's this trade-off. Right? Does anybody happen to remember from last semester, like what is the optimal angle for the trade-off? If you want to send it the furthest distance, what angle?
45.
It is 45 degrees, 45 degrees, right? And there's a proof for that too. It's probably on Google Classroom way back. Okay. Yeah, 45-degree angle. That's like the optimal angle for that trade-off. All right, so we've got 40 degrees. Okay, so let's focus on the vertical stuff and figure out how much time is it going to be in the air. Okay? Now, there's more than one way to do this. Right? So somebody tell me, what is one equation that you could set up to determine how much time it's going to be in the air? Yeah.
D sub f equals v naught plus at.
You could do that. Oh, actually, I'm looking at my solution from yesterday. I did this. Okay, yeah, I did a version of this too. Right. So final velocity in the y direction is equal to initial velocity in the y direction. Maybe I'll say minus gt, or some version of that, right? It's okay. You should say plus at, but it's going up, gravity's pulling down, handle the negative. Okay. Now, this is just a formula. We can turn this into an equation if we plug in numbers. And even still, there's more than one way to do this. So, Elijah, which way would you have gone with this? Like, what numbers would you plug in?
For the final velocity, I would plug in 0. The initial velocity, I would plug in the 64.3.
Mhm.
Then the gravity would be 9.8.
Okay, actually, that's exactly what I did yesterday too. Okay, so let me tell you two different ways you could do it just from the front. And you could have picked different. Let me do it. I'm trying to give you guys a big picture of many different ways you can solve this. You guys know, let's ignore this equation for a minute. Right? You guys know y equals v naught t plus 1/2 at squared, something like that. Right? Guys, if you go from beginning to end, what's the change in vertical displacement? Is it 0? Right. So you could have also pulled out that expression, right? The displacement, and said the displacement vertical would be 0. You could solve it that way, right? Or you could pull this expression. And what I just said to do, what I did too, is I didn't actually do the full hang time, right? Is I just went from this point to the peak at the very top, right? Because if you do that very conveniently, guys, what is the vertical component of velocity right at the very top? 0. And that's why Elijah's saying to plug in 0 meters per second here. Okay. Yeah, not the only way to solve this, but this will work, right? And that's why I chose to do it too myself. And it was going 64.3 meters per second vertically initially. Okay. Yeah, you can pick either 9.8 or 10 meters per second squared there. I just said 9.8 meters per second squared, so go do that. Okay. You get t. Now this t, I'm going to throw a subscript on this t. Okay. This is t to get to the peak, right? Not the full hang time. Isn't that true? Right. Now, if you did want to go ahead and set this up so that you could solve for the full hang time, how could you change this equation so that t came out to naturally be the full hang time? There's a way to do it.
You just multiply the t value by 2.
Yeah, okay, yeah, that's kind of the path that we're on. That's what we're going to do, right? But how about this? Think about symmetry. Right? We're ignoring air drag. It was initially going up at 64 meters per second. When it's crash landing, is it also down 64 meters per second? So could I put like a negative 64.3 meters per second here? Right? If you put in negative 64.3 meters per second here, then that gives you the full hang time. Okay, that's just another way to do it. But let's do it this way because I like this way too. So I can add this over, divide by 9.8 meters per second squared. So t to the peak is 64.3 meters per second divided by 9.8 meters per second squared. Right? The negatives go away because you like add stuff over. Right? And let's see if this is right. 64.3 over 9.8. I'm looking at like 6.56 seconds. I know we've got some rounding going on, but right. So that's to get from here to here. Right? So from the cannon to the peak. Right. We guess. All right. Now, take this the rest of the way here. All right. So if the time to the peak was 6.56 seconds, right? How do you get the full hang time again?
You multiply by 2.
Yeah, 2 times the time to the peak. Okay, so let's just multiply that by 2. Right, times 2. I'm looking at like that looks about right. 13.12 seconds. Right. So that cannonball from blast point to crash point has been in the air a little over 13 seconds. Right, 13 seconds. Right. Okay, we're getting real close to the end. All right. The question is like how far downrange was land? What's its horizontal displacement? So what do you do next? Exactly. Right. So everything we've done so far is all vertical motion. Right. The vertical motion is going to determine well what we figured out, the hang time. Okay. Now we're going to switch over and go horizontal. Okay. We're going to say x equals v sub x times t. Right. Horizontal displacement is how fast it's going across times how much time. Okay. So we got was it 76.6 meters per second going across the field. And we did that for 13.12 seconds. So we get here 76.6 times 13.12. Right. I'm getting 1004.99, I thought 1005, right? And that would be meters. Right. So just blasted it about a kilometer. Okay. Right. Any questions about that process? You guys can handle projectiles? There we go. All right. To show you guys my solution yesterday. I'm going to do this myself. Again, it did really similar thing here. Okay. So I let the final velocity go to vertical component velocity go to 0, so you can get the time to the peak. Right. Multiply that by 2 to get the hang time. I was using 10 meters per second squared initially, right? And then okay, so this is all vertical motion to determine the time. You switch over to horizontal. Right? X equals vt on the horizontal direction. Right? And if you did use 10 meters per second squared, then it's not going to go quite as far because I'm assuming gravity is slightly stronger. Right? So maybe it's a little bit short of a kilometer. Right? Oh, and then there you go. Exactly what we got if you use 9.8 meters per second squared. Okay. You guys get that? Okay. Projectiles. All right. Okay. Any questions so far? All good. All right. So let's switch over to AP Classroom questions. Okay. So you guys have a quarter page in front of you, right? You guys got a quarter page? Okay. So on this quarter page, write your name. Okay. I'm going to pick this up from you guys. I'll have you guys score yourselves as we go along. Okay. Write dynamics 1. Okay. We did this a few weeks ago for kinematic motion. Okay. So we're going to do dynamics now. Guess we got a little kinetic practice today, right? The projectile. Okay. And number this, let me check. I think it's 1 through 20, I want to say. Did I just lose? Hold on. Let me pull up over here on the screen. Okay. To just start numbering, we're going. Oh, whoops, got here. All right, assignments. Got a lag here. It's working. Dynamics 1. Yeah, 1 through 20. Okay, can you guys number 1 through 20? 1 through 20. All right, number 1 through 20. All right, and we're gonna start tackling these. All right, so I'm gonna switch my screen over and we'll get going there. All right, so number 1 through 20.